Assalamualaikum guys, my name is Ateeb Sohail and I will be hosting the next two sessions on IGCSE Computer Science. I've done sessions previously in our IGCSE and regarding computer science I'm quite good at it. So this session we're going to be doing chapter 1, chapter 2, chapter 3 and parts of chapter 4, and the remaining is going to be left for the next session, which is going to happen tomorrow at this exact same time. Right, so will the session be enough to prepare for the exams? Now obviously it's almost impossible to do 3 years worth of syllabus, 2 years worth of syllabus in 8 hours, so we're going to try to do as much as we can, but most likely for every chapter we're just going to cover the surface of it. Okay, we're not going to dive too deep into that, but it's a good revision session. It'll be a nice revision of everything that we've done so far in 2 years. Okay, so yeah, okay, let's begin. So when we talk about the syllabus, the first thing that comes to our mind is chapter 1, that is data representation. Alright, now when we talk about data representation, there are some number systems that come to our mind. These of course being the main one, the one that we all love, the one that we see in hacking, binary. Alright, and then the numbers, denary, and then the kind of numbers and a combination of letters, hexadecimal. Now these three number systems, we call them base and then the possible values that they have. So it's like, for instance, in binary you have a 1 or a 0, okay, a true or a false, a yes or a no, an on and an off. Okay, that's why we call it base 2, because there's only 2 possibilities. In denary we call it base 10 because it is 0 through 9. In hexadecimal we call it base 16 because it is 0 through 9. It is 0 through 9 and it is A through F. Okay, remember to always do this as capital. Okay, so when we talk about these three number systems, we want to know that this is basically how the computer works, and this is basically in our syllabus. The first thing that we're going to cover is basic conversion between these three number systems. Now you should obviously already know how to convert between all of these, but we're just going to go over them real quick. Okay, so when we talk about binary, we know that it's just going to be a combination of a bunch of ones and zeros. Okay, and these ones and zeros are just used to represent whatever hexadecimal value we have, or whatever value we have, denary, hexadecimal, whatever, right? So when we talk about binary, okay, let's just take any binary number, like for instance 1100. Now there's two methods that people use when it comes to converting between binary and denary. Okay, now the most fastest method is of course the subtraction method. Okay, especially when you want to convert a denary value to a binary value. Okay, so let's just say that you have the number 49. Okay, now one thing that you need to know, that you should know, is the powers of 2 all the way up to 512. Okay, so you have 512, you have 256, you have 128, you have 64, 32, 16, 8, 4, 2, 1. Now obviously you're not going to be allowed to use a calculator in the examination, so it's important that you have like those quick mental math skills. Okay, so you have a number such as 49. Basically you want to go through this list till you find the next number that is smaller or equal to the number. Okay, and you want to keep on doing this till you have 0 left. So like for instance we have 32 over here, so I'm just going to subtract 32 from this, and that will leave me with 17, right? And now I look at the next number. The next number that's smaller than 17 is 16, so I'll just subtract that and I'll be left with 1. Now the next number that is lesser or equal to that is obviously 1, so I'm just going to subtract 1 and I will be left with 0. Now you can see that there are 3 possible combinations of 1s. Okay, so all we have to do now is to compile this. Now in the examination, most likely you're just going to be asked up to 8 bits. What does that mean? It means that in the exam something like this is going to appear. Okay, so like you're just going to have to be focusing on 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what we're gonna do is you should always write your answers in 8 bits as well. Okay, so like for instance this number right over here, we're gonna start at 128. Okay, I'm just gonna remove these guys for now. You're gonna start at 128. Was there 128 in the number? There wasn't, so we're going to write a 0. Remember, 1 0, 1 means on, true, 0 means off or false. Okay, so we just basically said that in the number 49 there's no 128. Now let's move over to 64. There's no 64 either. 32, we did subtract 32, so we're just going to write a 1 over there. Then 16, we did subtract 16, so we're going to write a 1 over there. Now 8, there was no 8, there was no 4, there was no 2, and there was a 1. So right here we have the binary value for the number 49. So this is the subtraction method. The other method is called the division or the LCM method. That's basically taking the number, dividing it by 2, and getting the remainder. So like 49 divided by 2 would be 24, remainder 1. Divided that by 2, you get 12, remainder 0. Divide that by 2, you get 6, remainder 0. You divide that by 2, you get 3, remainder 0. Divide that by 2, you get 1, remainder 1, which can be rewritten as top to bottom. So 1 1 0 0 0 1. And remember, always set it to 8 bits, so you just add 2 zeros at the back. So you can see that the number is the same whichever method you use. These were the two main methods for converting a denary into a binary. Now, when we want to convert a binary into a denary, we follow a similar scheme. Okay, so like let's just take the number, this number right over here, this number that we have, 1 1 0 1 0 1 0 1. Now, one thing that you want to know is that you're counting positions from right to left. So this right over here, this is position 0. This right over here, this is position 1. This right over is position 2. This is position 3, 4, 5, 6, 7. And since this is a base 2 system, we're basically saying that this value is equivalent to 2 to the power of 7, 2 to the power of 6, 2 to the power of 5, 2 to the power of 4, 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, 2 to the power of 0, which is why I said you should have these values memorized. 1, this value right over here stands for 1, this value stands for 2, 4, 8, 16, 32, 64, 128, and you go on and on and on, right? So I told you that you basically want to imagine this as if there's a 1, then that number contains the denary value that is associated, the 2's power that is associated with that number. So if you look over here, you can see that there is a 1 right over here. Okay, so let's just do 1. Okay, so because there's like this is 2's power 0, so 2 to the power of 0 is basically equal to 1, so we are just doing 1. Okay, so 1, and then this is 2, there's no 0 here, so we're gonna skip that. Then this is 4, we can see there's a 1, so we just add 4. Then there's 8, now 16, there's a 1 over there, so we're gonna do 16. Okay, and then 32 is, we're gonna skip 32, we're gonna do 64 and 128. Another method that teachers use when they go about this is to do multiplication. So like 1 times 2 to the power of 0 plus 0 times 2 to the power of 1. This is extremely long, which is why I don't advise using it. You should have these values memorized on your fingertips by now. So yeah, you should probably opt for the subtraction method. You should practice the subtraction method. You should have it on your fingertips. The 2's powers, you should have them on your fingertips. 1, 2, 4, 8, 16, 32, 64, 128. At least till 128, right? So this is basically how you convert between binary and denary. By the way, if you guys have any questions at any time, just send them in the live session, the chat in the live session, and I'll have a look at it immediately. Okay, so all right, moving on, let's take a look at conversions between binary and hexadecimal. Now, when we talk about binary and hexadecimal, simple thing. The first mistake that I see people do is they try to memorize the table. You know, everybody's seen the table in the Hodder book. But when we converting to binary, don't we do 1 divided by 2, 0? That's the LCM method. That's what I was talking about right over here. Okay, you have a binary number, any binary number. You, like for instance, you have 84. Divide that by 2, you get 42. Remainder 0. Divide that by 2, you get 21. Remainder 0. Divide that by 2, you get 10. Remainder 1. 5 remainder 0. 2 remainder 1, 1 remainder 0, 1 0 1 0 1 0 0, and you add a 0 at the start. The reason that I don't like this method, I'm sorry, the reason that I did do this method, I think you're a bit confused, but the reason that I don't like this method is because I find it quite tiring and time consuming. This method right over here, if you're fast enough at math, then you can basically just look at the binary number and just deduce the denary value of it. Like if you give me a binary number, I don't even write anything down, I just deduce a binary value of it. This method, it's much more complicated. Though I always suggest that you guys like try to use both methods if you have the time, of course. But this method, I always recommend this method because it's fast, plus you can do it in your mind. All right, so let's move on to the hexadecimal. So as I was saying, when we talk about hexadecimal in specific, there's things called there's this table in the Harder Education book. Now many kids, they just memorize the table, go to their exam on the blank page, and I'm telling you this from like my classmates as well. They memorized the table, went to the last page on the examination sheet. The thing that they memorized, they just wrote it down, and during the examination they just copied from it. Now that's not exactly conceptual at all, so let's see how hexadecimal basically works. Okay, so one thing that you need to know is that each hexadecimal character, just memorize it as 4 bits, okay? Meaning that x, okay, where x could be a 1 or a 0, okay? Now, 0, 0, 0, 0, you could remember hexadecimal like you remember denary, okay? So we already know that the numbers 0 through 9, okay? That is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0 1 1 0 0 1 1 1 1 1 0 0 0 1 0 0 1. We already know that this is 0, this is 1, this is 2, and so on, right? So the only thing left are the alphabets, okay? Just imagine, just keep on going like that, okay? Just keep on like thinking the denary value of the alphabet as well, okay? So like for instance, you have 0 through 9 over here. Now I'm gonna continue till like we're at the maximum thing possible. Just give me a sec. 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Right, so now you can just remember that A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, and F is equal to 15. Now obviously I'm not saying to like just memorize this and then again go to the blank page, write this down, okay? This is things that you should have like in your mind. It should be implanted in your brain, okay? You should know that C is 12, D is 13, E is 14. It's basic conversions between a number and binary, okay? So yeah, you just want to basically make sure that any binary number you have, you divide it into groups of 4, and then you convert it using this thing that you have in mind, okay? Like for instance, let's just spam any random keys, okay? Any random combinations of 1 and 0, okay? No matter how long the number is, you just want to start from the very right and then go 4 bits and then like create a divider. Like for instance, 4 bits, I created a divider. Another 4 bits, I created another divider. Another 4 bits, another divider. Another 4 bits, another divider. Now this number was chill. It gave us the number of bits in a multiple of 4. But if, let's just say, the examiner does something like this, all you have to do is add 2 zeros to the left. You don't even have to do this, but if you like find it like confusing, just add 2 zeros to the left, okay? Remember, in binary, no matter how many zeros you add, it doesn't matter as long as it's to the left, okay? So yeah, so 1 0 1 0, we already know that is A, okay? 1 0 1 0, that is 8 plus 2, so 10, A. 1 1 1 0, that is 14, so E, okay? 0 1 0 1 is 5. Then again 0 1 0 1 5, 1 1 0 1 is 13, so D, and then 0 0 0 1 is 1. So this is basically our hexadecimal from a binary number, okay? And to like convert from a hexadecimal to a binary, we just follow the exact same process, just in reverse, okay? So like for instance, you have a binary number such as AF8. We know A is 10, so we just write 1 0 1 0, okay? 8 plus 2, that gives us 10. And then we just write the value of F, which is 1 1 1 1, 15, and then 8, which is 1 0 0 0. Now obviously it's not going to be like perfect for assembly today. It's not going to be perfect, so it's going to be like repeated practice that you guys do, okay? Whether that's on past papers and whatnot, okay? So, and we're going to try to solve some past paper questions as well throughout the session, okay? So that is conversion between binary and hexadecimal, binary and denary. Now let's look at conversion between denary and hexadecimal. Now there's 2 ways that people approach this. The first way, again, the quite complicated way. I honestly never thought to use this way. I found it really stupid and way too long, is to divide it by 16 and take the remainder. You know, a similar thing to what we did while we were converting binary and denary. Like for instance, let's just say that you have a number such as 612. What happens now is that I would need to bring out my calculator because even my mental math isn't that strong yet. I honestly never understood why my teacher, will there's, yes, it will be, don't worry. It will be shared with you guys. So I gotta take out my own calculator because I've never used this method. But basically, divided by 16, okay? You just want to divide it by 16. I believe you get, let's see, not 40, 37, 38. Okay, you get 38, and then the remainder is, I believe, 4. Okay, the remainder is 4. Please, I apologize if I get this wrong. This is why I don't like to use, yeah, exactly, this is why you should not do this method, though people still teach it, so I'm still teaching it. Okay, and then you have 2, which is going to be the remainder for that is going to be 6. So the answer is 2, 6, 4, and of course hexadecimal. Now the other method, the easier method, you know, why make your life so complicated? Convert this thing to binary and then convert that to hexadecimal. 612. This is why I asked you guys to like memorize up to 512. Okay, so 612, 512, we know that's going to be included, so we write a 1. Okay, so 512. Okay, and then we subtract 512 from 612, you get 100. Okay, so 512, then you come 256. Nope. 128. Nope. 64. Yes. Subtract that, you get 36. All right, so 64, 32 is indeed, so we just subtract 32, you get 4. Okay, 0, this is 16, 8, 4, 2, 1. So this is your binary number. Okay, now just add the dividers like I told you guys. 0, 0. Okay, and now just convert this in normal way. 2, 6, 4. Yeah, exactly. Simple thing. All right, so remember, it's better to be right in the longer way than to take a stupid risk and do the math. I don't really like this. I've never used this method, not in my CAIE, not in my normal examinations. It's stupid. So always go with this method right over here. Okay, I highly suggest this method, right? Just convert it to binary and then convert that to hexadecimal. Though, you know, if you want to act nerdy in front of the examiner, I don't care, do it, but always use this method to at least recheck once, because dividing by 16, you know, I had to use a calculator for that. All right, so that is conversion between denary and hexadecimal. And when we talk about denary to hexadecimal, hexadecimal to denary, just use the same method again. Okay, so like for instance, you have the same number 264, convert that to binary 0 1 and then you get 0 1 1 0 0 1 0 0. Just add the 2's powers and you get the original number. Or again, if you want to act nerdy, 2 times 16 to the power of I think 2 times 256 plus 6 times 16 plus 4 times 1. This is basically 16's powers, you know, 16's power 0, 16's power 1, 16's power 2. You will get the same exact answer. 512 plus 4 plus 6 times 16, you should at least get the same. Yep, you get 612. So it's not always bad to convert to binary and then do the thing, right? It's not always bad that way. So yeah, either method works, and you could do either method. Anyways, that is the conversions. So let me try to see if I can bring out a past paper question, and like we can try to solve that. Let's see, row of papers. Let's take out any random past paper. Okay. Let's go with this one. Okay, March 2024. One more thing. If you understand the concept, I could give you any random number right now. For instance, 1,642,834,233. and with the help of a calculator you can convert that to binary. So if you understand the concept, you can basically do any number, okay, no matter how big, even if it's not in the syllabus. If you guys understand that, you understand the concept when you can convert anything, when you can do anything regarding that thing. And this is not just for computer science either. Anything, you understand a concept when you can do anything regarding that concept, or anything that actually uses that concept. Okay, now let's look over here. Okay, ASCII denary number. I don't think we've done ASCII yet, so we're gonna skip this for now. Oh my god. Okay, it should not have taken out a. I'm gonna just take out O levels for now. They don't have. Okay, let's see. Computer science. I think I opened computer studies. That would make so much more sense. I think I opened computer studies. I apologize. Okay, so right over here. Not our thing yet. Okay, tick one box to show which statement about the hexadecimal number system is incorrect. It uses the values 0 through 9 and A to F. That is correct. Okay. And they asked for the incorrect one. It can be used as a shorter representation of binary. That is correct. Why do we use hexadecimal? Because if you have a large as heck number, 0 1 0 0 1 0 1 0 1 0, of course I'm not gonna go to my colleague. Like, let's just imagine this for a sec. Your computer gives you the blue screen of death, or it shuts down, or something, an error occurs, and on the screen is written 0 1 1 0 1 0 1 0 1 1 0 1 0 1 0 1 1 1 0. Imagine you have to call tech support for that. You call them, hey bro, there's like this error on my screen, 0 1 1 1 0 1 0 1 0 1 0. You'll sound like a freaking robot. So that's why we have hexadecimal. Hexadecimal is basically a shorter representation of binary. Okay, instead of reading all that 0 1 0 1 0 0 0 1 1 0 1 0 1 0, you just be like, yo, there's this error on my computer, 0xabcde, right? Simple thing. All right, so you don't have to be all robotic and all of that. All right, so then it is a base 10 system. This is the incorrect one. Why? Because we learned that denary is the base 10 system because it only has 0 through 9, but hexadecimal is base 16 because it has 0 through 9 and A through F. Now let's look at this, actually the thing that we just did. Okay, so convert the three denary numbers to hexadecimal. Let me take a screenshot of this and we're gonna go over to freeform. This is my first time I'm using this software. Last time I remember I was on Windows. So much of an easier user experience because like that was touchscreen and this is not touchscreen, so sad life. Okay, convert the three denary numbers to hexadecimal. Okay, so first of all, you got 20. All right, so the method that I told you guys, listen, all you have to do, don't make it complicated for yourself. You could do this in your brain. Okay, simple thing. 20 into binary, you could do the rough working. There's obviously gonna space for rough working right over here, working space. 20 into binary is 1 0 1 0 0. All right, just add a few zeros before that. Okay, so 1 2 4 8 16 blah 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 blah. All right, I just converted this to binary. You guys can use the longer method. Okay, you guys can use the long method. I just converted this like to binary and just convert this to hexadecimal. Remember, 4-bit caps, but add a divider in between. 0 0 0 1 is 1, 0 1 0 0 is 4. So the answer for the first one is 1 4. Also, please don't go around saying like it's 14 in hexadecimal. That's being stupid. It's not 14, it's 1 4. You're basically saying that 20 is equal to 14. It's 1 4. It's not 14, it's 1 4. Okay, so next you had 32. 32 would be 1 0 0 0 0 0 0. All right, just add another 0 before. So that, add a divider, you get 4 0. So 4 0 is the answer for the second one. All right, and lastly you have 165. See, that's what we call big numbers. So okay, so you have 1 and then you got a 0 1 0 0 1 0 1. Add a divider in between. You get 8 plus 2 10, which is A, and then 0 1 4 plus 1, which is 5. So A 5. These are your answers for this question. Basic stuff, okay? Basic stuff. Now, if I open up the marking scheme, because obviously I doubt myself, who doesn't? It should be 1440A5. Where is it? 1420A5. Yeah, see, this is why you doubt yourself. I probably messed up. Yeah, see, my bad, guys. It's 0010. Yeah, it is 20, not 40. See, this is why you check the marking key. Yeah, I messed a space here. This is the 32 one. So, yeah, exactly. This is why you always check the marking scheme when you're doing this. Anybody can make a mistake. Could we be asked to use a specific method for converting? I've never seen that happen. No, because normally what they do is they give you the numbers and then below you have the working space, so you get the marks for writing. So like for instance here, they don't, in the marking key they don't have it specified what method you use, so any method should work. Okay, doesn't matter. Okay, the only thing that matters, the only time the method actually matters that I've seen so far is binary addition, and we're gonna get to that in a sec. Okay, so as I was saying, I'll just put this over here for now. Let's move on to the next topic, which is going to be the uses of hexadecimal. Okay, we just did conversion. Let's move on to a small topic, basic yapping. Not too much, easy. Okay, so uses of hexadecimal, and where did my text box disappear off to? Okay, there it is. Uses of hexadecimal. Now, one thing that I told you guys already is basic stuff, how you don't want to be going around saying stuff like 0 1 0 1 0 so and so on. So there's 4 main uses of hexadecimal. Okay, the first one being error codes. Okay, error codes. Second one being IP addresses, and there's 2 types of these. We're gonna dive into them soon: IPv4 and IPv6. Third one being MAC address, and fourth one being HTML code. I'm not gonna write their definitions here like I told you guys at the start. Not a deep lecture, I'll just say it. Okay, so error codes, like I said before, imagine your laptop dies. You have a whole number. Okay, 0 1 0 1 blah 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 blah. We convert that to hexadecimal. It's just in hexadecimal. Okay, even right now, if you guys have like a old laptop, and you smack it so hard on the keyboard, and I'm telling this from experience, you smack it so hard on the keyboard, it gives you the blue screen of death. In the bottom left, or even if I just Google right now, the blue screen of death, okay? Blue screen of death, Windows 10, right? Where is it? Show me the blue screen, bro. You know, the sad smiley face type thing? If you look over here, you can see, never mind, they don't have it here. See, this is why you like Linux. I swear to God, they used to have it in Windows 7. Anyways, point is, you get an error code like ABF6721 blah 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 blah. Okay, that's an error code. It's normally in hexadecimal. That's the first usage of hexadecimal thingy. Used to have what? Error codes. Okay, error codes. That's the first usage. Okay, because you don't want to go around, you don't want to create a whole ass operating system just to tell people that you have the error 0101000011 blah 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 blah. Okay, you want to have a small error code, something that I can easily Google as well. So that's basically error codes. That's the first usage of hexadecimal. Now, when we talk about IP addresses, someone said his chat for IP it's only IPv6. I'm unsure about that. IPv4 and IPv6 I'm pretty sure is included till the 2026 syllabus. I'm pretty sure it even came in my examination. IPv4 is in our syllabus. It came in May, June 24. There was a question regarding IPv4. They asked you to give an example of it. So IPv4 is included in our syllabus, especially in O levels. No, I can tell. Okay, yeah, for hexadecimal it's only IPv6, but IPv4 in general it's included in our syllabus. Okay, IPv4 in general is included in our syllabus. Right. So when we talk about IP addresses, you have 2 types, IPv4 and IPv6. Just by the name, you can already tell that IPv6 is the newer one. The newer kid. IPv4 is the older kid. Now, if you guys were to Google my public IP address and you were in you have like a cheap ISP or something, you'd probably see something like 1110 plus 90 plus 90.32, something like that. Okay, that is called an IPv4 address. Okay, now there are some characteristics of IP addresses that you guys need to learn. Okay, so for instance, IPv4 it's separated. IPv4 is separated by dots, full stops, periods. Okay, should probably add brackets around there. IPv4 is separated by dots, periods, whatever you call them. Okay, and one more thing that you have to know, it is a 32-bit number. 32-bit number, and the maximum value that you can have as a number inside of here is 255. All right, that's the biggest value that you can have in there. Okay, 255. That is also the biggest value that can be represented by a binary number that is 8-bit long. So if you were to convert this to denary, you would see that it's 255. Okay, so when we talk about IPv6, an example of IPv6 is something like A8FB, or even like B467 colon F7666 F666 A78A. You get the point, right? 000000000, and I think it's like 1 2 yeah, it's 8, so 111F, right? It's something like this. Okay, so in IPv6 is separated by semicolon, okay, sorry, colon. All right, and it is a 128-bit number, and it's basically broken down into 16-bit chunks. Okay, how is it 16-bit? Remember, one hexadecimal character is equivalent to 4 bits. So if we just count, basic counting, right? Basic counting over here. If we just count 4, 8, 12, 16. 4, 8, 12, 16. 16 times 8, 128. All right. So one thing that you have to know about about IPv6 is something called zero compression. Okay. It's basically the fact that, let's just see, you see right over here, there's a string of zeros. We can rewrite this to be you can rewrite this to just being a double colon. Okay, just like that. Okay, and that basically signifies that it's a series of zeros. Like for instance, if you were to magically have an IPv6, please don't use this as an example. If you were to magically have an IPv6 something like this, okay, let's just say that, you know, you're like the creator of internet or something, and you have an IPv6 like this, you could write it as you could just write it as BF67 double colon A777, because the double colon, it basically specifies that it's a string of zeros. It's a bunch of zeros combined together, mushed together. That is what we call zero compression. Now next up you have MAC addresses. MAC addresses are basically addresses that are assigned to the network interface card. Okay, NIC, network interface card of a device by the manufacturer. One more thing to know about IP addresses is the difference between static and dynamic. Static IP address, as suggested by the name static, doesn't change. A dynamic IP address, on the other hand, it does change. Okay, every time that you, like for instance, let's just assume that your local computer has the IP address, local IP address 192.168.10.1. If you have a static IP address set for that computer, it will always stay that. It will always be 192.168.10.1. But if you have a dynamic IP address, maybe every time I close my Wi-Fi and turn it on, I'll be assigned a new IP address. Okay, that's the difference between static and dynamic. So a MAC address is an address that is given to the NIC by the manufacturer. It's rarely ever changed. So the MAC address on my Mac from like 3 months ago is still the same. Okay, I didn't do some crazy shit to change that shit because I don't go snooping in the hardware. It's rarely ever changed. Okay, and it's in the format, you can say AA colon AA colon AA colon AA, sorry, BB colon BB, where AA is basically manufacturer ID and BB is basically what do you say, the device ID, the device model ID, right? Basic stuff. Okay. So an example could possibly be 00409696 colon A1 67 colon 88 colon C9, something like this. Okay, that's a MAC address. Is MAC assigned on the NIC? It is assigned on the NIC, on the network interface card, by the manufacturer. So for instance, if you have a computer, let's just say it's made by Dell, everybody knows what Dell is. The network interface card inside of that computer is going to have a MAC address that was assigned to it by the Dell company. Okay, that's why I said AA, BBC, AA and BB. This is basically the manufacturer ID. This is basically the ID of the device itself, the serial number of the device, you can say. Okay. Don't they ever run out of possible codes? Give me a sec, I'm reading something. One sec. Okay, so a MAC address, of course they do run out of codes. Okay. But you could think as a MAC address is more of like a device-based ID. Okay. You use an IP address to identify a device on a network, and a MAC address for that as well. Okay. But you could think of MAC addresses more as like something that was assigned to a device in specific. Exactly, it's mostly important on the network. Like, I don't really know how to explain it. Basically, MAC addresses is basically assigned to a device in specific. Okay, an IP address is given to a device that is connected to a network. Okay, that's basically the difference between MAC and IP. And next up you have HTML color codes, last usage of hexadecimal. You know, almost every color you see, will this get covered again in chapter 3? Probably, yeah. We're gonna go into a deeper depth there. Okay, so HTML color codes, basic format RRGGBB, where R is red, G is blue, green, B is blue. Okay, if you go on to Google, MAC is equal to hardware, IP is equal to software. Not exactly. I'll explain this more in chapter 5 and chapter 3. Okay, don't worry about it. All right. So if you go on to Google, okay, and you just type any random hex code right now, you'll see it gives you a lovely color. Hey, it's actually a lovely color, and this is basically called an HTML color code. It comes in that format, the format that I just showed you guys, RRGGBB, where each of these is the value of red, green, and blue in the color. You know the primary colors, red, green, blue? That's basically this, okay? So any color that you see on the internet, any on your screen, that kind of stuff, it is a hex code probably. Like for instance, y'all's role ID, it has a hex code. My role ID, my profile picture, all of this, it's a hex code, right? It can be described as a hex code, okay? So this is basically HTML color codes, okay? An example would be like something like FF0000 even, meaning that it's just pure red. Next up, let's see. Next we got the most boring, long, weird topic, binary addition. Now someone asked me earlier, does the working matter? In the case of binary addition, I'd highly suggest that you show the working, the binary working, all right? And you should do the 2's complementing. You should do the negative thingy. You should show the working in that case, especially when they say show the working. Okay, I'm gonna show you guys the method to reconfirm and a method to do it. Okay, and honest opinion, should I do past papers or watch this session? Okay, so if you do past papers, don't do past papers. If you already know all of this, do past papers. If you don't, watch the session. Alright, you have to know the advantage and disadvantage of dynamic and static and dynamic IP. I believe I saw a question regarding that once. We're gonna go into the depth of both of those in chapter 5 or chapter 3, right? So you don't have to worry about it right now. We're just doing chapter 1 for now. Okay, we're just doing chapter 1 for now. That's why this is like the basic covering. Okay, but I do believe I've seen a question regarding those. So binary addition, lovely It's a love-hate relationship between me and binary addition. I remember like having a huge ass binary number 0 1 0 1 0 1 0 1, and I needed to add it to 0 1 0 1 0 0 1. Okay, and I was like, hell no. So I just thought to myself, it's binary, it's addition, why don't I just convert it to denary and just convert that to binary again. And apparently that is exactly how it worked. So let's first look at the how this addition works. Let's just look at binary addition between two small numbers for now. Okay, for instance 0 0 1 0 0 1 1 0 1. Okay, so 1 0. Now this is a thing, this is some rules that you should have memorized. 1 plus 0 is equal to 1. Carry, I'll write the carry on the right side and the sum on the left side. Okay, 0 plus 1 is equal to 1 0. 1 plus 1 is basically equal to 0 1, and then 0 plus 0 is equal to 0 0. Now I'll explain this rule in a sec. Okay, so imagine you have a number like this. You want to start from the right. Okay, you want to add these two numbers and you want to start from the right. Okay, so 1 plus 0, it is 1 and there is no carry. So what I'm going to do is I'm going to write 1 here. Similarly here, 1 plus 0, same thing, 1 0, it's 1. Okay, same thing here, 0 1 0 1 1. All right, and then again you got this. Okay, and if I convert this to my lovely old denary number based system again, you have 2 over here and you have 8 9 10, you have like 13, I believe. Yeah, 13 over here. Okay, 8 plus 4 plus 1, you add these two, you get 15, which is equal to this. Okay, so you convert it to denary when you want to recheck, and let it stay in binary when you're doing the actual working. What's the difference between HTML and Python? That is sorry, that is not in our current chapter yet. Not what we're doing right now. But in general, HTML is a markup language, not really a programming language, just a markup language. And Python is an actual programming language. HTML is mainly used to create web pages. Python is mainly used to create actual programs. So yeah, there's a huge difference. HTML doesn't require a compiler or interpreter, something like that. Python does. That's basically the difference between these two. HTML is a markup language, Python is a programming language. Anyways, right. So this is basic stuff. But let's just say that you have a carry now. Let's take a number 1 1 1 1 1, and let's take another number 0 0 0 1. Now, if we convert this to denary real quick, you'll see this is 15, this is 1. So the answer should be the denary value 16. But try to represent the denary value 16 using 4 bits. You won't be able to, because it would be 1 0 0 0 0. That's 5 bits. We're talking about 4 bits. Now this will cover two main topics in binary addition. The first one is the carry thing. So 1 plus 1, that is going to be 0 carry 1, meaning that we're going to carry a 1 right over here. Now you have 1 1 0. So first you do this thing right over here. 1 plus 1, what is that? That is 0. So, and carry 1. So I'll just carry 1 in advance to the right, to the left side. And now I have 0 over here. So 0 plus 0, that is 0. Next up, 1 plus 1, 0. And a carry of 1. So I just did carry 1. Okay. And 0 plus 0, 0. Same thing here. Okay, 1 plus 1, a carry of 1. Okay, I'll just move these guys a bit to the right. Okay, so a carry of 1, and 0 plus 0 is equal to 0. Lastly, 1, and you can just imagine this as zeros. Okay, you can just imagine this as zeros. Okay, you don't need to imagine this as anything. So 1 plus 0, 1. 1 plus 0, 1. 10,000. Or sorry, my bad. 1 0 0 0 0, and this is 16. Okay, so what just happened here? The first thing that we did was learn how to do addition of 3 binary digits. The second thing we learned is the overflow error. When you have a number that is like, let's just say I have another number, a binary number, 1101, okay, 1110, and I have another number. If I add these two together, it will not be 4 bits. It will not be 4 bits. Okay, because if you go over here 1 2 3 4 1 2 3 4, it will instead be 5 bits. Okay, probably it should be 5 bits. Yeah, all right, so it will be 5 bits or 6, I'm unsure. You do the math. Okay, so it won't be the product, the sum of these two numbers, it won't be 4 bits. There will be an extra bit, just like how there was here. If I suddenly remove these zeros, okay, you'll see that this is 5 bits, not 4 bits. So this right over here, this is what we call an overflow error. Overflow as in there is an overflow of the binary numbers. There's an extra binary number. So that's basically an overflow error. Okay, so that is binary addition. Yeah, so you should use this method when you're working, and you should use this dendry method when you're rechecking. Okay, so yeah, let's move on to the next topic. That is going to be binary shifts. Ooh. Oh man. Okay, look, imagine you have 3 binary numbers. Okay, in order to calculate 3 binary numbers that are in a column like this, all you have to do, ignore the last one for now, focus on these two. What is 0 plus 1? 0 plus 1 is 1. So just imagine this as 1. Now what is 1 plus 0? 1. So the final answer would be 1. If you have something like 1 1 0, what is 1 plus 1? That is 0. So just imagine this as 0. But remember, there is going to be a carry, so you just move 1 over to the left place. And now 0 plus 0, that is 0. So this is the answer of 1 plus 1. 1 0. You understand that now? 3 binary digits, 3 bits. In order to add 3 bits together, just go from top to bottom. Do the top and bottom one, to the top and to the first and the second, and then the answer to the first and the second, do it with the third. If you have a number such as 1 1 1, okay, this is actually quite a confusing one. Okay, so make sure to bear along with me on this one. You have a number 1 1 1 1. Okay, all you have to do here is okay. So what you want to do? 1 plus 1, 0 carry 1. Okay, now what is 0 plus 1? It's 1. So yeah, see, now you see a large number like that and you think, oh shit, we're screwed. But no, it's actually really simple. All you have to do is go from top to bottom. If I have a large as heck number, all right, we just did like 4 bits. If I have a large as heck number like this, and I have another large as heck number like this, okay, 1 2 3 4 1 2 3 1 2 3 1 2 3 4. Okay, let me just add some nice spacing in between so my OCD doesn't get triggered, you know. Okay, and you want to add these two numbers. Let's have a look. Okay, so 1 plus 1, that is going to be 0. Okay, and that is going to cause us to carry a 1. Now let's just imagine that this was also 1. Okay, I'm just going to imagine that this was a 1. Okay, so 1 plus 1, that is going to be 0. So I'll just imagine this as 0. Okay, and I'll carry 1 because that's what we learned, right? So now 0 plus 1, that is 1. So 1. Same thing here. 1 plus 1, 0 carry 1. So I'll just add the carry. Okay, and then 0 plus 0, 0. Same thing over here. You carry 1, and then you add it. You get 0. Same thing over here. You carry 1. You add 0. Now here 1 plus 0, 1. 1 plus 0, 1. And then same thing over here. 1 plus 0, 1. So that is going to be your answer. Do you understand it now? Okay. Let's see. Just give me a sec. Okay, so imagine you have a binary number. Okay, now there's two types of shifts. Okay, there's right shift and there's left shift. When we talk about left shift, okay, we basically mean to remove the bits on the left and then replace them with the ones on the right with zeros. I'll explain in a sec. Imagine the question says shift this number 6 places to the left. Now that's absurd and stupid. but let's just say if it says shift this number 6 places to the left. What you want to do, look at the left. 1, 2, 3, 4, 5, 6. Okay, let's just yeet these guys out of here. I should probably not. Okay, 0, 1. We just yeeted the guys on the 6 on the left. Now what we're gonna do, we're just gonna replace them with a bunch of zeros on the right, and bada bing, bada boom, you got your shift. Okay, right over there, that's your shift. Now, an important concept here is to learn the value, or basically, listen, when bits are shifted to the left, bit shift to left, you wanna basically multiply the number by 2. Okay, to the power of whatever the shift was. Okay, to the power of n, where n is number of places, and bit shift to the right is basically divide the number by 2 to the n to exponent n, where n is number of places. Okay, so right over here we had this binary number, lovely little binary number before we ruined it, as 17. Now we shifted it 6 places to the left. Now 2 to the power of 16 is 64. Okay, wait, hold on, I think I did something wrong. Hold on. Give me a sec. No. You're supposed to remove from, you're shifting to the left, so you're supposed to remove the ones from the left and then add it to the right. Let's take a smaller example. Hold on. Let's take a smaller example. Let's do 1 place to the left. You get the original number 17, shift that to the left, you get 0, 0, 1, 0, 0, 0, 1, 0. Let's see. So is that 17? Yeah, that is 17. That gives you let's see, 32 plus 32, 34. 17 times 2, 34. That works. Okay. Why didn't that one work? Hold on, give me a sec, guys. 17. Oh, okay. Sorry. Right. So, okay. So basically, I just realized what I did. Just deal with small numbers. Okay. You got like 0, 0, 0, 1. Okay. 0, 0, 0, 1. Okay. Shift this 1 place to the left. You get remove the 0 on the left. Yeet it out. Replace it with the 0 on the right. You get 34. Or if they said 2 places to the left, which is, this is also equivalent to 17 times 2 to the power of 1. We shifted it 1 place. So if you do it to like 2 places to the left, you get 0, 1, 0, 0, 0, 1, 0, 0, which is equivalent to 64 plus 4, 68, which is basically 17 times 2 to the power of 2. Okay, so if you do that 17 times 4, you get 68. Okay, and if you shifted 3 places, the reason that it didn't work before was because it would, if you shifted 6 places to the left, you would get 1, 0, 0, 0, 1. Okay, and then you would get hold on, actually 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. This would be your answer. You just add zeros to the right. Okay, you add zeros to the right and you just shift it to the left. Okay, that's it's kind of, yeah. Okay, so this would be your answer if you shifted it 6 places to the left. If you calculate this real quick, so 1, 2, 4, 6, 8, 1, 2, 4, 8, 16, 32, 64, 64, okay, 64 plus 128, 256, 512, 1024. This gives you 1088, 1088, which is equivalent to 17 times 2 to the power of 6, I believe. Yes, right? So you add the amount of zeros to the right for whatever n places are to the left. Okay, so multiply, yeah, okay. So for if any number that you have, just add zeros to the right, the amount of numbers that there are. Okay, they're obviously not going to ask you to shift 6 places, something like that. They're probably going to ask you to shift small places like 2 or 3 or even 4. but probably not like that many places. Okay, you just add zeros to the right, the amount of zeros that you require. Okay, that's on me, guys. And in the case of shifting to the right, if they ask you to shift a number such as 0 1 0 1 0 1 0 0, and they ask you to shift this number two places, hold on, let's just cut this out. They ask you to shift this number two places to the right. Get rid of the two zeros on the right, so you're left with 0 0 0 1 0 1 0 1. And the denary value for this would be 16 plus 4, 20 plus 1, so 21, which is equivalent to the original value. Okay, so this right over here is 64 plus 16 plus 4, 84. And if you divide 84, so I told you guys, divide the original number with the 2 to the power of n, where n is the number of places shifted. So if you divide 84 by 2 to the power of 2, alright, so 84 divided by 84 divided by 4, you'll get 21. 12. Wait, no, sorry, 21. Yeah. You get 21. Alright, so basically, when you're shifting to the right, divide. When you're shifting to the left, multiplication. Do we need to actually do the multiplication of the division? They can ask you for the value. I've seen questions like this, especially in IGCSE. I've seen questions like this. Okay, they can ask you for the value after shifting. Maybe they don't ask you to write the new binary value. Instead, they directly ask you to write the value. So you should know this. Okay, you should know this. But I personally, I don't think I've seen it in O levels, but I'm pretty sure I've seen it in IGCSE. Let me actually check. Can you do an example question for past better? Sure. Just give me a sec. Let me just confirm this. Okay. For me too, logical shifting was yes, we're getting to 2's complement soon. Okay. My Wi-Fi is so slow. I'll take out the past papers till then. Let's see if I can find one. Let's see. Nope, not in this one. Let's try summer. Let's see. Nope, not in this one either. Let's try variant 2. I don't think it was in this one anyway. Yeah, I gave this one. No, wait, did I? Yeah, I did. Oh, this is traumatizing to look back on. Okay, let's see. I should probably have had some topicals before coming in here. Okay, let's look at variant 3. Okay. Oh, finally. Okay. So let's see. Where is it? Okay. And if you go over here, let's see. Yeah, you guys should probably know. Yeah. See, understand the effect that this has on the positive binary number. It's in both syllabuses. Yeah, you guys should know the multiplication and the division thing. Okay, you guys should know that. right? It's in both the syllabuses. Don't worry, you ain't getting out of this one. But yeah, let's check this one out. Let's see. Why am I unable to find? Oh my god, I'm just gonna make up an example myself. Okay, I'm gonna tell you guys a past paper example myself. So you have a binary integer number 010010. Part A is to shift 2 places to the left, and part B is to find the denary value of the above shift. Now for part A, what you want to do is you want to basically well, of course, add 2 zeros to the right. Okay, so 0 1 0 1 0 0, or actually I'll make this even simpler for you guys. I'll get rid of this one. Okay, so just yeet the two zeros from the left side, 0 1 0 0 1 1, and then add 2 zeros to the right. This is going to be your your places shift to 2 left. Okay, so 2 places to the left. And to find the binary value of the shift, all you have to do, take the original number, convert this to denary. You get I'm pretty sure you'll get 16 plus 2 18 19. So now just multiply 19 by 2 to the power of 2. Okay, so you'll get 76, I believe. So 76 would be your new value. Okay, so this is the type of question. This is going to be like 2-3 marks at most. Okay, this is the type of question. 72 19 times 4. I think it's 76. I think it's 76, not 72. Yeah, 76. Yeah, okay. So if you actually convert this number right over here, you get 76 as well. So 64 plus 8 plus 4, you'll see 76 as well. Okay, so that is basically how a past paper question regarding shifting would look like. And oh my god, gotta bring these down. Holy cow. All right, let's move on to the fun part. Holy cow, this board is gonna be long as heck. Why couldn't I have started at the top left actually? Let's see. Oh, there is no top left. Oh, okay, that makes so much more sense. Okay, so let's I apologize guys, this is like my first time using this software after like such a long time. All right, let's see. Hello world. Okay, there we go. All right, so let's look at negative binary numbers. You know, by how long is this session gonna be? Hopefully till hardware. Do we have to know binary subtraction? That is actually an excellent question. I don't think it is in the IGCSE syllabus. It's in the A-level syllabus, but not in the IGCSE syllabus. Pretty sure it isn't. Yeah, add 2 positive numbers. No addition of, no subtraction in binary. That is A-levels. That is A-levels, my guy. You're thinking way too far ahead. You gotta slow the pace down. You're being way too much of a seasoner. You gotta slow. Yeah, exactly. It's not even in the syllabus. You gotta slow your pace, man. Come on. Why are you trying to increase the threshold, my guy? Anyways, as I was saying, so negative binary numbers. Okay, so if I give you guys a number such as negative 68, how will you convert this to a binary? Now, of course, we can use the same methods as before. All right, you can use the same methods as before. Okay, but this time what you do is you take the very left thingy, the register on the very left as negative. So like for instance, if you're doing a 8-bit number, you know that this goes like 1 2 4 8 16 32 64 128. So all you do is 1 minus 128 64 32 16 8 4 2 1. Okay, now all you have to do is like do the same thing. Okay, so you always write 1 minus 128 as 1, and what you do now is you have 128. Okay, so now you add 64. Okay, right. Okay, so 64, adding 64 will mess it up, so we're gonna skip that for now. And now what you want to do, let's see, 32. Okay, so this is just basic mental math. Okay, so you get minus 96, then you add and then you add 16, so you get minus 80, then you add 8, you get negative 72, you add 4, and then you get negative 68, and then you just do 2. Okay, so this is going to be your negative number, and you can reverse process this by doing minus 128 plus 32 plus 16 plus 8 plus 4. You will get you should get at least Negative 128 plus 32 plus 16 plus 8 plus 4, you should get negative 68. This is the basic method, okay? So it involves a lot of mental math. The more common method, and the method that you should use when they say show you're working especially, is the 2's complement method. How does 2's complement work? Now, you know, the first thought that came into my head when I heard the word 2's complement was the guy who invented that, was he named 2? And personally, I never thought to Google that question because I thought it was way too stupid, and I was in class and we weren't allowed to use phones in class. So yeah, if you guys are interested in that, just Google it. I never Googled it. But anyways, so imagine you have a binary number such as negative 68. Let's just take negative 68 again. Okay. Which topics will be covered in this stream? Chapter 1 through 3, hopefully, inshallah, and then if we have time, chapter 4 and chapter 4. All right. So negative 68. What I want you guys to do, forget about the negative sign. You know, forget about your problems. Anybody can do 68. Some people can do negative 68. So just forget about the problems. Convert this bad boy to binary. You will get 0, 1, 0, 0, 0, 1, 1, 0. Sorry, no, 0. Yeah, okay. You'll get this number. Okay. So what you want to do now is you want to be sneaky. How will you be sneaky? Well, simple. You want to basically invert the things. Okay. You want to invert the number. Like for instance, you have 0, 1, 0, 0, 0, 1, 0. You want to invert all the ones in the 0. So it becomes 1, 0, 1, 1, 1, 0, 1, 1. Now what you want to do is you want to be even more sneakier and add 1 to this. So 0, 0, 0, 0, 0, 0, 0, 1. You want to add them, okay? So you want to be sneaky as heck. You want to add 1 to this, okay? Now what will happen? 1 plus 1, 0 carry 1. So there's going to be a carry right over here of 1. 1 plus 1, 0. 0 plus 0, 0. Carry 1. So now you get 1. Then 1. Then 1. Then 1. Then 0. And then 1 again. And now you will see it's the same number as above. So this is the method that you want to use in your examination. And when you're done with this method, just recheck. Minus 128 plus 32 plus 16 plus 8 plus 4. Just recheck using the method above. Alright, so you want to use the 2's complement method always. They're going to tell you to use the 2's complement. Always use 2's complement. Okay, and recheck. So you just invert the note. Yes, exactly. You invert the normal January number and just add 1 to it. Okay. Oh, it's the same guy who carried the von Neumann infrastructure. Boring guy. The guy was such a big CS nerd, bro. Oh well. Anyways, as I was saying, yeah, in the binary number, yeah. The guy was a nerd, though. I'm gonna be real. You should, when they ask you to use 2's complement, always show the carry working as well. Always. Okay. So anyways, moving forward, that is binary, that is 2's complement done as well. So now we're actually gonna move to the fun conceptual part, hopefully. And what we're gonna do is we're going to do text, sound, and images. Lovely. Okay. There is one thing that I want to check real quick. Just give me a sec. Okay, got it. Okay, so negative 72 is just verify it yourself. Do minus 128 plus 32 plus 16 plus 8. Yeah, it is negative 72. Let's do ASCII code. Yes, sir. You know, you should know the value. I'm gonna give you guys a simple trick. If they ever ask you to convert this shit, because February, March 24, those guys asked to convert an ASCII letter to binary. Okay, and I was so confused. I didn't even know that was in the syllabus. So, yeah, I'm gonna give you guys a simple trick. Okay, basic stuff. You have a binary number. Okay, let's just say you have a binary number. And that, wait, hold on. There's something weird with the order book. Give me a second. Okay, sorry. So you have a number. Where did my freeform go? Let's do ASCII. Okay, so when we talk about ASCII, you want to know, first of all, everybody should know the full form of ASCII. American Standard Code of Information Interchange. You know, the one thing that I thank the Americans for, the ASCII. Whenever you click a key on your keyboard, okay, whenever you click a key on your keyboard, that key gets converted to binary, and then using ASCII, it's shown on your screen. Like if I'm clicking right here, it's a bunch of zeros and ones, you know, 0 1 0 1 0 1 1 1 0 1 0 1 0 and so on. It's ASCII that you guys see. By the way, can you clear up? So they say when a binary starts with 1, they'll always specify when it's a negative number. They'll always specify when it's a negative number. They'll always specify it's a negative number. They'll say that this is a 2's complement binary, or that it's a negative number, blah blah blah. Or maybe they show you minus 128, or they highlight the 128. Okay, they'll tell you. Okay, I'll show you some examples later on. Okay, so American Standard Code of Information Interchange. Now, even Cambridge is not that stupid to ask you guys special characters. So what I'm gonna do is I'm gonna tell you guys something. There's two things that you want to learn: uppercase and lowercase. Uppercase begins at 41, I believe, and lowercase begins at 61. Now, we all know the alphabet. I don't think anybody here failed primary school. We all know what it is. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. And for ABC, and for the capital A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, Q, R, S, T, U, V, W, X, Y, Z. Now, the one that I showed you above, this is lowercase, this is uppercase. Okay, so I'll just do this. Okay, so imagine they ask you to convert the binary number LMNOP. Exactly. Imagine they ask you to convert the letter N to American Standard Code of Information Interchange, capital N. How do you do that? Well, 41. Now, A is basically 41. This is A, and this is lowercase a. Okay, so how many letters away is N exactly? Let's just look. So this A is 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, and this is 54. Okay, so it's a 54th number. Okay, sorry. No. Sorry, my bad. Uppercase starts at 65 and lowercase starts at 97. Sorry guys, that's on me. I was wondering why it didn't start at 65. Okay, so it's actually this. Okay, my bad. Okay, so 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78. So we now know that N is 78. Okay, you don't need to memorize every single one of them. Just memorize one of them and just move on from there. You just need to memorize A and then just write the alphabet and just go 1 plus 1 plus 1 plus 1. Okay, so N is 78. Now just convert that to binary. You get 0 1 64, 78 minus 64, that is 18 minus 4, 18. Okay, so says 14 0 0 1 1 1 0. This is your value for N in binary. Just memorize the beginning of lowercase and uppercase A and you should be good. Okay, this was a past paper question indeed. Yes, February, March 2024. We just saw it. All right, that is ASCII for you in a nutshell. Okay, there's obviously other characters, but I don't think even Cambridge is that evil. I don't think even Cambridge is that evil to give you those special characters. Just give me a sec. All right, I'm back. In my mind, if Cambridge does pull off a stunt like that, do we need to know ADV and what do you mean by, oh, you mean advantage and disadvantage? I don't even think there is an advantage or a disadvantage. We're forced to use ASCII. We're forced to use ASCII. Everything uses ASCII. ASCII is just the standard, the industry standard. All you need to know is that it's the industry standard. Okay, it's the industry standard. It contains a bunch of letters. You should know the definition. You should know the definition. Okay, it's basically it's a system that was set up for communication between computers. Okay, comparison between Unicode and ASCII. That is an excellent question. Just give me a sec. Let me switch to water. Exact. Okay, yeah. That. Okay. So, as you can expect, ASCII was made by people who spoke English, so they focus on English mainly, whereas Unicode is more expanded. Okay, it's a larger, and it's more efficient. Okay, it's more efficient, larger. Okay, now you should know the disadvantages and the advantages. You should know the comparison. Basically, okay, let's write this down actually. Diff between. So Unicode, it's basically a universal standard. Okay. Furthermore, it's more efficient, and it's basically either 16-bit or 32-bit. Okay, Unicode, and yeah, it has way more. It's way more. It has way more. Of course, don't write it with like that many bytes. Just say that it's like slightly. It's more expanded than ASCII, right? So yeah, that's basically the difference between ASCII and Unicode. Next up, we got the lovely chapter, sound, images, and I'm gonna complete this thing in like 10 minutes. So I want you guys to listen to me real carefully, okay? Real carefully. So let's talk about sound and images. Alrighty, let's see. Okay, so there's a type of images. We call these bitmap images. Okay, bitmap image. This is basically an image that is made up of pixels. Okay, and pixels are basically picture element. Okay, pixels can be defined by a hex code. Okay, so or anything, to be honest. Okay, pixels are basically colors. Okay, they're basically colors, red, green, blue, blah blah blah. It's a it can take like multiple shapes. It could be in circles, could be squares, rectangles, you know. If you have a phone right now with an old crappy phone with an LCD display, and you look real close on it, like you bring your eye to the very edge of the screen, you'll notice a bunch of green, blue, and red things. Those are called pixels. Okay, I'm pretty sure that if you have an LCD display, you should be able to see them. Even if you don't, you should still be able to see that. Okay, what's extended ASCII? Basically ASCII with more stuff. Okay, as suggested by the name. Okay, so okay, so the pixels. Okay, so there's another definition. You want to know the definition of color depth? It's basically the number of bits that's used to represent pixels. Number of to each color, number of depth. Number of bits used to represent each color. So like for instance, if you have like an 8-bit color depth, that means that there is 256 colors. There's a possibility of 256 colors. Okay, so basically the larger the better. Okay, now another definition that you want to know is image resolution, which basically means number of pixels. Oh my god, number of pixels in an image. And lastly, I think that's it about, yeah, for images, and that's it. Okay, for images, that's it. Okay, so there's a formula. Okay, there's a formula. Now this formula, we basically use it to calculate the size, the file size. Are we going to do paper 2? Not in this session. We will do it in the future before paper 2 examination, but not in this session. Okay, so the formula to calculate the file size of an image is basically the resolution times color depth. For instance, if they ask you to calculate the file size of an image that has a resolution 1920 x 1080 and a color bit of 8 bits, all you have to do 1920 x 1080 times 8, just calculate that and put it in. That is your answer in bits, by the way. unless they tell you that this is actually byte. Okay, let's just say that they tell you to calculate the answer in bytes. Now, actually, I should probably not go into that yet. Just remember this basic thing, okay? I'll dive into bytes and bits later, okay? So just remember this basic thing, okay? So yeah, you just multiply it, okay? So you get times 8. That's the formula for file size of image. Now, in the case of sound, sound is also very similar. Sound is basically, I think you have to learn just 2 definitions in the case of sound. That is the sampling resolution, which is number of bits per sample. And you could also call this bit depth, by the way, bit depth. And lastly, you have, hold on. And lastly, you have sampling rate, which is number of sound samples taken per second. Alright, you should have these memorized. And lastly, the formula to calculate the file size of that is sample rate times, sorry, I should probably, file size of sound equal to sample rate in hertz Hz times sample resolution times length of sample seconds. All right, that's basically it's basic memorization. Let me know if you guys have any questions. How is analog anyways, okay, so let's talk about file sizes. File sizes. Okay, so you want to know what a KB, MB, GB, TB, PB, and EB is. Okay, let me name these. So you got kilobyte, megabyte. I'm just not gonna write byte. Okay, so you got kilobyte, megabyte, gigabyte, terabyte, petabyte, and exabyte. Okay, and then you have KIB, MIB, GIB, TIB. This was just some guy who decided to be fancy, okay, and wanted to invent his own system, so he did something really idiotic. I'm just kidding. PIB. Oh my god. And then EIB. Again, same thing, but Kibi, Mebi, Gibi, Tebi, Pebi, and XB. Now you should know these prefixes. So you should know these prefixes. Alright. When we look at kilo, mega, giga, tera, peta, exo, all you need to know is that this is 1000 bytes. Kilo is 1000 bytes. Mega is 1 million bytes. So 1 times 10 to the power of 6. Then 1 times 10 to the power. I'm just gonna write 10 to the power. Okay. So 10 to the power of 10 to the power of 3, 10 to the power of 6, 10 to the power of 9, 10 to the power of 12, 10 to the power of 15, 10 to the power of 18. Right. And when you come over to kibi, mibi, blibi, bibi, blah, 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 the thing about that is like some idiot wanted to show off. So what he did, he made a new thing and he said, don't follow the 10 powers. Do this shit instead. 2 to the power of 10, 2 to the power of 20, 2 to the power of 30, 2 to the power of 40, 2 to the power of 50, 2 to the power of 60. The guy's an idiot. The guy's an idiot. But of course, I'm gonna save y'all. The easiest way to do this, memorize 1024 and just multiply that every time. So like just do like 1024 times 1, 1024 times 1024 exponent 2, 1024 exponent 3, 1024 exponent 4, 1024 exponent 5, 1024 exponent 6. Now the reason I asked you guys to memorize it as 1024 is because the examiner is not as crazy as you guys think he is. He's not going to tell you to calculate like a large exact value and then divide it by. No. He's going to give you something. Like for instance, the question above, 1920x 1080 and the colored bit of 16 bits. He's going to tell you to give your answer in GB byte. So 1920x 1080 x16. Now this will give you your answer in bits. So what you're gonna do is you're gonna divide it. 1024 times 1024 times 1024. Because GB is basically 3, right? 3 of 1024. Okay. So now what you're gonna do is you're just gonna cancel it out. You're just gonna divide. Cancellation. 8, 512. 4, 256. 2, 128. 1, 64. All right, let's just get rid of this. 540, 32. 250, 260, 270, 16. And so on, right? So it goes on and on and on. You'll always find, oh sorry, yeah, times 8. You want to times 8 in both scenarios, okay? So the thing that I'm saying, you'll always find a way to cancel it out, okay? You'll always find a way to cancel it out. All right, and remember, these are bytes, kilobytes, megabytes, gigabytes, not bits. So if he gives you an image resolution or in bits, you want to make sure that you're multiplying it by 8. But if you get something like 16 bytes, in that case, you don't need to multiply it by 8. Okay, but let's just say it's bits. Okay, so remember to convert it to bytes. Okay, 1 byte is equal to 1 byte, 8 bits. And no, you cannot bring a calculator. They actually threw mine out the window. That was a long story as heck. That was the longest heck story. So yeah, please do not bring your calculator, guys, especially if you love it. All right, if you don't like your calculator, bring it along. They'll throw it out the window. But if you don't like, but if you do like it, but if you don't like it, just bring it along. If you do like it, please leave it at home. Let's talk about compression. Now, when we talk about compression, there's two types of compression. There's lossy compression, and then there's lossless compression. Lossy basically means that the original file cannot be recovered. Okay, but it also means that the data the size is significantly changed. An example of lossy file compression would be, I should probably zoom this in. Okay, so an example of lossy would be JPEG or MPEG-3/MPEG-4, or as you guys commonly know this, MP4, MP3, MP4. Okay, simple things. Now let's talk about these two files a bit as well. MP3 is basically used for music, and MP4 is basically used for video. Now, how does lossy compression exactly work, or any compression in general? Alright, so how do these files exactly work? Now, an MP3 file, it basically, let me give you an example. An MP3 file, it basically removes audio outside of the human audible range. Now, if I remember correctly, you know, physics days, that's 20 hertz to 20 kilohertz. So basically what it does is that anything that's outside of that range, it just yeets it out because you can't hear it. Okay, and like if two sounds are played at the same time, the softer one or the more quiet one is removed. All right, this is also called perceptual music sharpening or shaping. All right, and when we talk about MP4 files, almost the same thing happens. Okay, but instead of that, it also does like some pixels, you know, videos, blah blah blah. It basically reduces the quality, but to an acceptable amount. Okay, to an acceptable amount. All right, so I'm sure the calc is not allowed. This is like the number one thing that they tell you in like 01, that calculator is not allowed. Now, when we talk about lossless, what we're talking about in lossless is okay, so in lossless, the original file can be recovered. Now, the most popular lossless method is run length encoding, which is RLE. Okay, it basically means that let's just say you have a string or a pattern. okay, and you want to basically compress that, okay, they always tell you what the they always tell you the pattern. Like for instance, if you have a, by the way, I'm taking these, if you're ever wondering where I'm taking these examples out of, I'm taking them out of the Horror Education book. All right, so A, B, 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 C, C, D, 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 D. Now, we all know that the value of A in ASCII, as we learned above, is 97. B is 98. 97. B is 98. C is 99, and D is 100. So what we can do is we can say that there are 5 A's, 4 B's, 2 C's, and 5 D's. So we just converted this thing into this. See how simple that is? Easy peasy lemon squeezy. Easy peasy lemon squeezy. However, something like this would not be effective if you have a string like this, because what are you doing then? You're just doing 0 1 9 9 0 1 1 0 0 0 1 9 9 0 1 0. You know, you get the point. Okay, you get the point. All right. Do you have to remember letter values? You do not. I told you, just remember the starting value and just add to it one by one. All right. So that is run length encoding, patternization. And in the case of images, you just do black is equal to 1, for instance. Black is equal to 1, white is equal to 0. Sorry, black is equal to 0, white is equal to 1. And you can rewrite an image that has a bunch of black pixels. So like if it's like this, okay, if it's like 0 0 0 0 hashtag FFFFFFF, you could just write it as, you could just rewrite it as 0 1 0 1 blah 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 blah. All right, basic stuff. Okay, so that is the entirety of IGCSE chapter 1, I believe, that we've covered. We haven't gone into the definitions yet, and Huffman encoding. Anyways, we haven't gone into the definitions yet. This is the entirety of chapter 1. I'm going to take a 5-minute water break. I'll be back at by like 7:50, 7:51, something like that. All right, see you guys. Water. All see, where is it? Okay, so let's move on to the loveliest chapter of them all, data transmission. Wait, where's the, okay, there we go. Oh my god, this is so much work. Now this is why they call you the CS nerd. You know, when you guys get that A star, you want to ping me, you know, make me feel happy, you know. Yeah, I really appreciate it, you know. Anyways, data transmission. All right, so okay, let's see, let's just get rid of all of this junk. Okay, so yeah, if I figure it out, I will, don't worry. All right, data transmission. When we talk about data, the main thing that you want to know is data packets. Any information you send over the internet, it is broken down into data packets. Okay, these data packets, they're extremely small. I'm talking small, like 64 KIB. All right, 64 KIB type shit. Okay, now you want to learn the basic structure of the data packet. That is the header slash payload slash footer, or slash trailer structure. All right, the header basically, and you want to know what is inside each one of these. The header basically contains the IP address of the sender, IP address of the receiver, and the size of packet. All right, and the payload is the data itself. And then you have the trailer, which is basically, which contains a method of identifying the packet, identifying the end of the packet, because computers are stupid. It's not like I can just give them a candy packet with candy in it and they'll be like, if I give you guys a candy packet and you eat the candy inside, you'll know it's empty. But the computers, when they get that packet, obviously it's not candy, but when they do, they don't know when it ends. So you gotta tell them that it's ended, especially with routers. We'll get into that soon. All right. So method of identifying the packet and some form of error checking, like a cyclic redundancy check, a CRC, cyclic redundancy check. Oh my leg. Okay. So right, so that is basically the entire structure. Let's do something called packet switching. I think I gotta restart the program. It's lagging way too much. Let's see. Do you guys see the lag? Or is it fine? Is the stream fine? Okay. Alright, so let's see. Okay. Now, you want to know what a router is. A router is basically a device that receives and forwards a data packet and is used to is used to convert is used to connect to the internet. Alright, but you should just know the main definition, which is, this is the main definition, by the way. Definition: it is the sender, it basically the decider. I'll just include this above. It also decides where to send the data packet. All right. So now, when we talk about router switching in general, you want to know that, packet switching in general, you want to know that basically packets, they go through different routes. Okay, different routers. Okay, it's like if I want to go somewhere. Let's just say I want to go from my home to my friend's home. Now, there are multiple roads that can lead me there. Now, let's just say I'm going to his house for the first time and I don't have the Google Maps type thing. So I ask the people in between, what's the fastest way? I get out of my home, I go straight. There's either going to be a right or a left. There's a guy in the middle, he's like, go right. That guy right over there is the router, I'm the data packet. So I go right. Now, another right or a left. There's a guy over there, he says go left. I go left. And then so on, right, left, left. Right, left, right, right, left, right, till eventually I reach my final destination. Routers decide where to go, where to send a data packet to. Okay, routers decide where to send the data packet to. And this packet switching is basically a process. Hold on. Okay. Basically, packet switching is a method of data transmission in which data is broken down into packets and sent sent through a bunch of nodes. Now, nodes basically are the things between routers. Yes, exactly. So there's two routers. Let's just say I want to send a message to somebody. I want to send a message to Daud Sayyid. I click on my keyboard, I press A, and I hit enter in his DMs. What just happened? That A got converted into binary. That binary got divided into a bunch of packets. That packets went to my router. Now, from my router, it went through different nodes. Or other routers. Okay? Right? We call routers nodes. It went through different routers, different nodes, till eventually it reached Daud's router. And from there, it showed up on Daud's computer. Okay? So, a router is basically used when a router is used when you want to connect to the internet or connect to any network. Okay, so okay, and one more thing, in packet switching in PS, always the shortest path is selected. All right. However, sometimes packets do not arrive in the same order as sending, which is why we have a packet number in the header, which basically tells that I don't think I wrote it. Yeah, okay. Yeah, I didn't write it. which basically tells the sequence number, which is basically the number at which the packet is at in the sequence. Okay, so the router is assigned the path before the router is. I guess you could say that. Yeah, you could say that. I guess you could say something like that. But they're basically forwarded when they finally reach the router. That's when they're decided where to put forward to. All right. So that's basic packet switching. Now the benefits of it. All right, you want to learn the benefits. Is that it's easy, it's fast, right? And there is no need to tie up. There is no need to tie up one line. And in case of faulty or failure line, if case of faulty line, another route can be chosen. But the drawbacks are that packets can be lost and there is a delay at the destination. Now a question that could arise from here is why is there a delay at the destination? Imagine I have 7 friends. I line them all up in a row and I put them in a maze and I tell them to get to the other side. Now they all leave the same way, but they all take different paths. Okay, let's just say I have like a multiple paths, multiple exits. They'll all eventually reach, but there is a chance that they don't arrive in the maximum possibility in the short in like the same order. Now let's just say one guy arrives there first out of the 7. Can I effectively say that all of them arrived? No, which means that the first guy who arrived and anybody else who arrives after that have to wait till all 7 of the guys reach. That is why there's a delay. If I break something up into 8 packets and I send those 8 packets, I cannot know what the original thing was until I get all 8 packets, and I can't get those until all of them arrive, which is why there is a delay at the destination. All right, so let's okay, so right, okay. And what about lost packets? Lost packets is basically packets that get sent throughout routers and then more routers and then more routers, but they just never reach their destination. Okay, to overcome this, there's this technique that we use. It's called hopping. All right, every time that a packet leaves, every time a packet arrives at a router, a hop number is decremented by 1, right? So for instance, if I have a packet, it goes to router 1 and it is in syllabus. It goes to router 1. I'm pretty sure it is. Oh my goodness. I swear to God I learned this stuff. It's even in the horror book. What the heck? Oh, you're right. Nice. You should still kind of know what it is, okay? Basic stuff, right? It just helps you understand, grasp the concept, alright? So, hopping is basically just like you send a number, and every time that it reaches router, it basically decrements by 1. So like, for instance, at router 1 it's 10, then router 2 it's 9, 8, 7, 6, 5, 4, 3, 2, 1, and if the hop number ever becomes 0, the packet is asked to be resent. Okay? Now, when we talk about data transmission itself, 2 main things: serial slash parallel, and duplex slash half duplex slash full duplex. Simplex. Alright, full duplex is the same thing as duplex. Alright, so when we talk about serial slash parallel, basic things. Serial basically means that one bit is sent along one line at one time. Parallel basically means multiple bits along multiple lines at the same time. Alright. Full duplex basically means that data is sent in both directions at the same time. Bits are sent. Bits. Half duplex means bits are sent in both directions but not at the same time. And simplex means bits are sent in one direction only. Now, a common example of screen is not being shared. Oh, shucks. No, stupid Mac. Headphones are dying. You should have been here in May, June 2024. I think we had one of the session had 56 people in it, all listening to me yap about computer science. It was of wild times. We used to bully the business students as well. Like just spam raid their VC while they were studying. Anyways, okay. You can read on this, just let me drink some water. Read on this. Okay. Imagine, hold on, let me see if I can. Okay. Imagine you have a sender. Okay, imagine you have a sender right over here, you know, and you have a receiver. I think this is the stream working. Oh shit. Switch screen. Is it still not working? Can you guys see the board? Can you guys see the board? I'll try resharing. Okay, great. Are you guys able to see the whiteboard? Right over here. Is the whiteboard visible? Okay, great. Now, imagine you have a sender and a receiver. Now, let's talk about serial first. Serial basically means that the data is sent along one wire only. Okay? Which means that every time that somebody has to transfer a 0 and a 1, it goes one wire. At this, not at the same time. So 0, then 1, then 2, then 3, then 4, then 5, then 6, then 7. Sorry, 0, then 1, then 0, then 1, 1, 0, 1, 0, one bit at a time. Where in the case of parallel, there are actually multiple lines. Right, so there's multiple of these lines. You know, multiple of them, and the bits are basically sent along these lines at the same time. So 0 could be sent through here, 1 could be sent through here, 1 could be sent through here, 0 could be sent through here, and so on. Now, obviously, serial is faster, right? But the problem with parallel is that it causes data skewage. Okay, so serial is faster. Sorry, serial is slower. However, parallel causes data skewage. Now, what is data skewage? Imagine I have a bunch of friends, and I and I put them on one corner of my room, and I tell them to run to my other corner of the room. If I send them one by one, I am guaranteed that the order they arrive in at the other corner of my room, it will be the same as the order they left. But if I tell them, go at the same time, there's going to be there's a small possibility that one of them arrives at a later order than the other. That's basically data skewage. Data skewage is when data does not arrive in the correct order. Bits do not arrive. Bits do not arrive. Bits do not arrive in the correct order. Alright? So, let's talk about full duplex, half duplex, and simplex. For this, all we need is one line. Imagine this one line. If I can only send data from sender to receiver, that is called simplex. This is commonly used in walkie-talkies, right? You know, hello, this is Rick, over, where only one side is sent data to. Half duplex on the other hand, basically it means that data can be sent forward and backwards along the same line at the same time. Sorry, not at the same time. Full duplex basically means that data can be sent both ways at the same time. Okay, basic things, basic memorization, you're just gonna have to memorize this. Okay, so what was I gonna say? Okay, so that's basically it. That's the types of data transmission. Okay, that's the types of data transmission. Then, all right, so okay, all right. So as I was saying, okay, I think I covered this thingy. Okay, I probably covered this thingy. Yeah. Okay, so as I was saying, data skewage is when the packets don't arrive. All right. So, where was I? Okay, universal serial bus. First, let's talk a bit about the advantages. Okay, of serial, or like just comparison. Okay, let's just compare them. Serial has less risk of interference. Parallel is faster. Serial is more reliable over long distances. Parallel works good over shorter. Serial does not have a risk of skewage. Parallel has a risk of skewage. Serial is used when amount of data is small. Parallel is used when speed matters, or basically they want it fast. And serial is less expensive. Parallel is easier to program. Let me know if you guys have any questions or if we should move on. Hopefully the comparison was easy to understand. Okay, let me know if you guys have any questions. Okay, all right. So, let's see. Okay. Skewage is basically when bits don't arrive in the same order they were sent. Okay, they basically arrive out of synchronization. Okay, so let's talk about universal serial bus. Oh man, I'm already so tired. Yes, it is. It's gonna be given to you guys. All right, let's talk about universal serial bus, or as we all know it, USB. Now, USB, I'm not going to dive deep into depth. We're just going to talk about the advantages and disadvantages. Okay, when you're using a USB, first of all, just by the name, it's serial, uses serial transmission. Okay, and it has 4 types of wires. It has positive, negative for both data and for power. Okay, and lastly, let's talk about the advantages. Device auto detects USB. Chapter 2, honestly, most of chapter 2 and chapter 3, basically everything besides chapter 1 is going to be memorization. So you're just going to see me yapping and writing a lot of stuff. So if you guys ever have something that you don't understand, let me know. Device auto detects USB. Connections fit in one way only. Industry standard. Supports different data transmission rates. No need for external power. Easier to add more ports using hubs. Backwards compatible. Drawbacks are standard USB has only 5 meter max length, no longer. Very old USB are not supported, and the newer USB models are still pretty slow. Okay, so all you have to do about USB is memorize the advantages and the disadvantages. Okay, now let's move on to the actually fun and long part. All right, so methods of error detection. Again, we're not going to dive deep into this. I expected to spend like 2 hours, 1.5 hour, 2 hour on data representation, but I want to finish this chapter in 30 minutes at most. Okay, so Methods of error detection. When we talk about the methods of error detection, there is like a lot of ways, especially during transmission. Okay, the first one is parity checks. When we talk about parity checks, is that really, you guys can hear me, right? You can see my screen as well. Yeah, okay. So when you talk about parity checks, parity can be either even or odd. For instance, if there is a number like this, and they say it's an even parity, you want to count the number of ones. 1, 2, 3, 4. This means that the data has arrived correctly. Or if there's a number, or if it's the same number, and they say it's an odd, you want to count the number of ones again. It's 4, so that means that this is incorrect. The data arrived wrong. As you can expect, it's stupid. The second thing about parity checks is called the block parity check. What that is basically you have a huge ass block. So like, let me see if I can. I don't even know if I can, like, I'll remind me later during past papers. It's gonna be in past papers. I don't know if I can draw that right now, if I have the mental capacity to do that right now. Okay, so basically how that works is that you want to look for the column with the broken thing and then the row with the broken thing and match the bit that's basically broken. Remind me to do that later. Okay, so parity checks, it can be either even or odd depending on the number of ones. All right, so next you have, pretty sure you have checksum. Now checksum is quite weird, like quite hard to understand. So you want to like listen to me, okay? But you want to more listen to me on this one, okay? So when a block of data is going to be like transported, a checksum, basically an expression is calculated from that block of data. So basically maths, all right? There's an algorithm that is basically agreed for by the sender and the receiver. And that checksum algorithm, that checksum value is transmitted with the block of data. Okay, then that checksum value, it arrives at the receiver, where the receiver uses the agreed algorithm that we just talked about earlier to make sure that the checksum value that has arrived is correct. And of course, if the checksum value is correct, then that means that data was transmitted correctly. If it isn't, the data was transmitted incorrectly. Okay, so then you have echo check. Echo check is basically data is sent back. If correct, data sent again. Sorry. If incorrect, data resent. It's literally like if I have a friend and he tells me something and I say it back to him, and he says it's incorrect, he tells me it again. You know, like if I'm saying something and he hears something else and he's like hello, and I'm like, did you just say hi? He's like, no, I said hello. Okay, similarly, hello, did you just say hello? And he just replies nothing back. That means that I did hear the correct thing. Okay, so that is echo check. All right, let's see. That is basically the transmission methods of the error detection. Okay, then you have the check digits. Check digits, there's two kinds of check digits. Right, there's ISBN 13 and there's modulo 11. Now I'm still unsure as to whether these are still included in our syllabus, but you know, might as well talk a bit about them. Okay, so I'll just talk a bit about them, just listen to me. Okay, so in ISBN 13, basically you want to take all the odd numbers. Okay, so ISBN 13, take all odd numbered digits together, and this is, by the way, their position. All right, the odd positions, and you want to add all, you take all even numbered digits and multiply it by 3. All right, so you want to you should know it. Like, I'm unsure if it's in the syllabus, so yeah. And then you want to basically add results, add these two and divide by 10. Remainder, take the remainder, and if it is 0, then use 0, else subtract from 10 and find check digit. Alright, so that's how you calculate the ISBN 13. And in order to check the ISBN 13, like recalculation, all you need to do is add recheck. You wanna add all odd number digits together, add all even number digits together, and multiply by 3. Add these two together and divide by 10. If remainder is equal to 0, then it's correct. You should know this, by the way. You should. I'm pretty sure. You cut off entirely for me. Don't worry, just go through it over the recording. It's fine. So basically, this is like the methodology. This is like how you calculate the check digit, and this is how you recheck the check digit. Okay. Then what you have next is modulo 11. In modulo 11, basically each digit is given a position and multiplied by it. Alright, or weighting, the weighting. So like it starts at 0 and then 1, 2, 3, 4 from the right. So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So like for instance, if you have a 7-digit number such as 4, 1, 5, 6, 7, 1, 0, the weighting values would be 8, 7, 6, 5, 4, 3, 2, 1, 0. Sorry, 8, 5, 3, 2. Okay. Then what you do, basically multiply. Okay. So 8 times 4, 7 times 1, 7 times 1, 6 times 5, 5 times 6, 4 times 7, 3 times 1, and 2 times 0. And then you just add that together. And then when you add it together, you divide by 11 and subtract the remainder from 11. Alright, so hopefully you guys got that. And for recheck, you want to basically same thing, give weighting, multiply and total, divide by 11. If remainder equal to 0, correct. Alright, basic stuff. You should know how to do this, by the way. Alright, then you have our lovely little ARQs. Automatic repeat requests. Lovely. Automatic repeat requests. ARQs. Alright. Automatic repeat requests or ARQs. Basically, there's either going to be a positive or a negative acknowledgement. Alright, and basically in ARQs, what do you say? An important thing to know is timeout. Timeout is basically the time interval allowed to elapse, meaning that allowed to go on before an acknowledgement is received. Now, the best way to understand this is if I send you a parcel. To your house, and I say you should reply back to me within 5 days if it has arrived correctly or not. 5 days is a timeout. If I send you the parcel and the parcel is correct, you send me back a positive acknowledgement. You're like, hey Atib, thank you for the parcel. It's fine. It's I. If it's incorrect, then you be like, yo Atib, you send a negative acknowledgement, right? You be like, yo Atib, the parcel you sent came damaged, bro. Can't tell you. I don't know what to say. Came damaged. But if you don't reply to me in 5 days at all, then I just resend you the package. All right. That's basically timeout and automatic repeat queries or requests. All right. So that should be it for data transmission. Now we move on to encryption, which is going to be the last topic of chapter 2. Okay, so there's two types of encryption. The first one is called the symmetric encryption. Symmetric encryption. This basically uses an encryption key. Now, one more thing. You guys, at the start of this lecture, I told you guys, the first thing I told you guys, this won't be in depth. Most of the important things, I'm just talking to you guys about it. I'm not even writing it down. The notes are only if you're watching this recording. That's the only use case that I see for the notes. If you're watching the recording and you want to keep up. Okay? That's the only use case that I see. So, as I was saying, there's two types of encryption. There's symmetric and then there's asymmetric. Alright, so in symmetric encryption, let's say I have a box. Inside the box are, I'll hopefully upload all of this by tonight, inshallah. Inside the box, I have a trophy. And I put this inside of the box. I lock the box with a key, and that is basically the key that you're going to use. Now, you have that key, and I have that key. Now, I just send this over to your house, and you unlock the same box using the same key. That's symmetric encryption. One key. Okay? So, for instance, let's just look at an example. Let's just say a team. However, A is basically equal to B, T is equal to A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, U, E is equal to F, and B is equal to C. Alright? We just moved it one place forward. So, the encryption key could be something like place is one more. So after encrypting, a thief could be B U F F C. Now to a normal guy, and especially when we're talking about why encryption is used itself, it's gibberish. But you have the encryption key. You know that every letter is just one ahead. So you just bring it back one step and you get a thief again. That's symmetric encryption. However, the more confusing thing, asymmetric encryption. Now, asymmetric encryption, it basically involves two keys: public key and private key. Now, basically, in this thing, okay, so I don't know how to write this, so you guys have to listen to me, okay? So, in asymmetric encryption, basically, there's like a public key and there's a private key. The public key is basically known to everybody, and the private key is basically known to only oneself. Okay, let's just say there are two, like me and you. Okay, now I generate a matching pair of keys. Okay, so I have a private key and a public key, and they're the same. I send you my public key. Okay, and basically now you have the document. You encrypt the document using that public key, and you send it back. Okay, send the ciphertext. Okay, so I'm basically sending you public key. You encrypt the document and then send it back. That's basically how asymmetric encryption works. Okay, private and public key is generated. Public key given to receiver. Receiver uses public key to encrypt and send the ciphertext, which is basically the encrypted text, ciphertext, back to sender. Sender uses private key to decrypt. That is asymmetric encryption. And with that, ladies and gentlemen, we close chapter 2 of IGCSE Computer Science.